So this is the lesson on power, which is on page 46 of your unit handout. We're just going to be defining what power is and solving problems involving power. Just here's the definition of power. The formula on your left is on your formula sheet. And I wish it wasn't. I wish the formula that was on your formula sheet is the one on the right. Okay? And I'll get to in a few minutes why this is the case. But the definition of power is the rate at which you do work, the rate at which you transfer energy. If I say, what is the rate at which I eat chicken wings on Friday night? The answer is going to be a number of wings per hour. It's going to be over time. If I ask you what is the rate, the average rate that you spend money throughout the week, it's going to be a number of dollars per day. Rates are typically, although when you get to calculus this isn't the case, rates are typically measured, the expression is with respect to time. We divide by time. So power is work over time. But since work is change in energy, there's no difference between saying power is work over time or power is change in energy over time. If you take a look at what we calculate for power, power is going to have units of joules per second. It doesn't matter whether you think of it as work over time. The units of work are joules, the units of time are seconds. Or if you think of it as energy over time, the units of energy are joules, the units of time are seconds. But rather than use joules per second, we use what's called a watt, which is abbreviated W. So here's the issue I have with the formula on the left. The formula on the left has a capital W. And this capital W is a quantity. It's not a unit, it's a quantity. And the quantity is called work. This capital W down here is a unit. So this is the quantity of work. It's a variable in an equation. The W for the unit is a unit of the quantity. But it's not the unit of the quantity work, it's the unit of the quantity of power. So very often when we're solving problems with power, I will just do the following. I won't use these formulas at all. I'll say power equals energy over time, or I'll say power equals work over time. I think in the end, though, you need to know that a joule per second is a watt. So on your formula sheet in the section titled Momentum and Energy, you see that formula power equals work over time. There are only two formulas in this section that you haven't learned about, and you won't learn about them this year. The two in the top left are concepts of momentum and impulse, which you would learn about in grade 12 physics. I realize that you are growing up in a world that doesn't have light bulbs that are rated at 60 watts or 100 watts. They're not manufactured anymore in what I would call the Western world. However, they are the type of bulb that was first invented before LED and halogen, and they are these types of bulbs. These are called incandescent bulbs. And they have a wire in them, and when you run electricity through it, actually that one's not incandescent. When you run electricity through it, that wire gets hot and it glows, emitting light. But if you've ever worked with these bulbs in any way, you know that there's a lot of heat. That if I turn this on and even leave it on for 60 seconds and I say, go ahead and unscrew that bulb, it's going to be very hot to the touch. And the reason why we don't manufacture these anymore in the Western world is that they're a waste of energy. Probably about 95 to 99% of the electrical energy that goes into one of these is lost as heat. They're very efficient if you want to heat your house. Just turn on 50 of these and the room gets warm very quickly. The only difference between this one, which is clear, and this one, which is frosted, is that the glass is literally frosted. It's got some coating on it, which provides a whiter type of light rather than the bright. If I turn this on, and maybe I will later and show it to you, this wire gets very, very bright. It's great for lighting up a large room if this is on the ceiling. But if you had this like on some type of lighting fixture on the wall, every time you turned your head towards it, you'd burn the retinas in your eyes. There's a lot of brightness, as well as a lot of heat. So, I can't read that. Might say 100 watts. What does a 60-watt bulb do, and what does a 100-watt bulb do? Well, very simply, a 60-watt bulb consumes 60 joules of electrical energy every second. And that means a 60-watt bulb produces 60 joules of light energy and heat energy every second. As I said, when we get to Physics 30, we talk about these types of bulbs because there's a physics discovery made that can only be made with these types of bulbs and not LEDs and not halogen bulbs or gas bulbs. It has to do with the fact that a glowing solid like that wire inside of the bulb produces a continuous spectrum of light. It produces every color in the rainbow, whereas an LED doesn't. It produces one particular color. Of course, then, for the 100 joules per second, you can simply replace this idea with 100 instead of 60 of light and heat each and every second. And again, with these particular bulbs, the bulbs are always rated with the amount of electrical energy you use. If you buy an LED bulb that emits the same amount of light as, say, a 60-watt incandescent bulb, the rating on that LED bulb may be only 4 watts. And it'll actually probably produce more light than a 60-watt incandescent. But LEDs don't get very hot. Okay. What are the units of power in standard units? Well, power is a watt, which is a joule per second. This is not something I would ask you on an exam. It's something that I'm warming you up to because it's a big idea in Physics 30. Okay? And I always go under the assumption that if you're taking Physics 20, you're going to continue on to Physics 30. These are units. This is not a formula with quantities. This is units. But although a second is a standard unit, a joule is not a standard unit. So how can we write a joule in standard units? The answer is to grab any formula you want that has energy in it. Because energy is what the units of joules give us. So I'm going to go with mgh. Would you agree that if I multiply mass by g times h, I get potential energy? And energy is measured in joules, which means that if I take kilograms times meters per second squared times meters, I have to get joules. I've gone from this equation that I'm highlighting in yellow, which is an equation relating quantities, to this equation in blue, which is simply a statement of units. I wouldn't even think of it as a formula or equation. It's just a statement. It says that a joule, 1 joule, is equal to 1 kilogram meter squared per second squared. Well, that means that a watt is equal to one of these, a kilogram meter squared per second squared over a second. And I realize that when you have stacked fractions, which we call complex fractions in math, it gets confusing for students, and that's why I teach this rule that will always work. Identify the denominator in this thing that you don't want to be there. And the denominator that we want to get rid of is this. If that weren't there, it would be a nice fraction to look at. So how do I accomplish that? I multiply the top and the bottom of this fraction by squares of seconds, or s squared. And that's going to accomplish canceling the seconds squared and giving you 1 watt is equal to a kilogram meter squared per second cubed. So what? I mean, if I asked you to explain what this means, you can't, can you? The purpose of doing this is not to come to some sensible expression for units for power. It's a mathematical exercise that leads elsewhere in Physics 30 and post-secondary physics. It makes much more sense to say that a watt is a joule per second. But by the time you get to Physics 30, you have to be able to do this. Okay. All right, let's look at some calculations here. I guess first we're going to talk about efficiency. When it comes to energy and doing things with machines, we have this idea called efficiency. And percent efficiency is the output energy over the input energy times 100. Very briefly. You understand that a machine is never 100% efficient. If I have a motor that's connected to some kind of chain on a pulley that's going to be lifting the forks on a forklift. Okay, it could be an electric motor, it could be a diesel motor, but I pick up a pallet of shingles and that motor grinds away, turning that chain, lifting that pallet of shingles, right? Do you understand that motor is going to get hot? Okay. That's because not all of the energy the motor is putting out is going into the useful task. So imagine that the energy that went into the motor was 10,000 joules. That's what goes into the motor. And that 10,000 joules is going to go out. But the useful output is what's important. If it's only 4,000 joules useful out, in other words, you find the potential energy of those shingles and it's 4,000 joules, and it required 10,000 joules, I hope you see this as 40%. So we would say that the motor, in regards to what it's trying to do, is only 40% efficient. And this is a Science 10 idea. So is power, by the way. You did learn about power in Science 10, but only trivially. Only in terms of this is P, this is W, find T. Let's take a look at some examples. An elevator and its occupants have a mass of 1,300 kilograms. The motor lifts, the motor that the elevator is connected to, lifts the elevator a total distance of 40 meters in 75 seconds. What type of energy transfer is made to the elevator and the occupants? Well, gravitational potential. Let's write this down first. EP gravitational. We've done enough of these elevator problems to know that although there is an initial amount of kinetic energy given to the elevator car to begin with, it moves at a constant speed throughout this long journey. So we don't worry about the kinetic energy. The elevator is not accelerating faster and faster and faster if it's going up or if it's going down. It's a constant speed. So that little tiny boost of kinetic energy, that jolt you feel in an elevator when it starts moving, is insignificant. So what is the power output? Well, power equals work over time. Again, I stay away from the formulas as they are on your formula sheet. Work is change in energy over time. What kind of energy is being transferred by the motor? Well, potential. We've already established that. And question B is a question you should be able to answer without being prompted to answer question A. You get my drift there? I shouldn't have to tell you it's potential energy. You should be able to figure that out. But the bottom line is we're going to end up with power equals mgh over T, which is certainly not a formula on your formula sheet. We built it, like we've built a dozen other formulas in this course. So what is the power? Power is the mass. I think it was 1,300 kilograms. As usual, I've run out of room here, so I'm going to abbreviate G. We know what G is. And then H, I think I remember 40 meters, but perhaps you can enlighten me on that. And I think I saw 75 seconds. Now, the nice thing about this previous question is we've already established that when you multiply these things together and divide by time, you get watts, right? We don't have to use the units here. We can just grab our calculator and figure out what this is, and we know the answer will be in watts. 1,300 times 9.81 times 40. And then, I mean, if I hit equals right now, this is the energy given to the elevator car and its occupants in joules. So I do not want the energy. I want to know what the power is. So I divide by the time, and I get 6,802 joules. Oh, we'll just say 6.8 times 10 to the 3. And I stopped short. I said joules, and I was going to say per second. And then my brain got sidetracked into the rounding. This is joules per second, or watts. By the way, 10 to the 3 is kilo. We could have just said 6.8 kilowatts. Are we okay with B? Yep, of course. What is the efficiency if the motor must generate 9.4 kilowatts of power to do the specific work? What this means is whether the motor is powered by electrical energy or diesel energy or traditional gas energy, you're consuming every second 9.4 times 10 to the 3 joules are consumed each second. But 6.8 times 10 to the 3 joules are used each second. Now, energy is conserved, so 9.4 times 10 to the 3 joules is coming out of the system each second. It's just that when we talk about what we're using it for, we're using it to lift the shingles. Where's the rest of the energy? Probably heat. No doubt about it. Not probably, heat. It's the only place it can go. So if you want to find the percent efficiency, you can take the power out that's useful over the power in. You could take the energy per second out over the energy per second in. I want to back up for a second. See, this formula is traditionally given by talking about energy. I don't think we need to take the power and multiply by 75 seconds to get the energy in joules and work with joules. We can work with power. And then, of course, we have to multiply that by 100. Can somebody give me an answer to the nearest even percent? 72%? Any other takers? 72? All right. So it's about 72% efficient, which is not bad. I mean, heat is the enemy Economically speaking, heat is an enemy. Environmentally speaking, heat is an enemy. The more heat we produce, the more money we spend on useless things, unless you're trying to heat a room. It's a heater, okay? Maybe then the heat is the useful energy. And the more heat we produce, the more we contribute to environmental problems. Number 2, a car accelerates from 10 meters per second to 30 meters per second in 6 seconds. What's the power? Well, power is change in energy over time. What kind of energy is the car getting from the engine? Kinetic, right? So this is going to be 1/2 mv squared minus 1/2 mv squared over the time. I don't know that this has come up. I don't think it has. You cannot just subtract those two speeds and do one kinetic energy calculation. It doesn't work that way. You actually have to go. I'm not going to write down the numbers. 0.5 times 1250 times 30 squared minus 0.5 times 1250 times 10 squared. So I'm just calculating the top of this. 0.5 mv squared minus 0.5 mv squared gives me this amount of energy. This is the kinetic energy increase of the car. That energy came from the engine. And it happened in 6 seconds. So it's about that many watts or joules per second. 83,333. Watts. I just don't like that capital W. I wish they would have called work something different, but they didn't. That W is not work. That W is a watt. If the engine is 42% efficient, what's the power of the engine? So what this means is 42%, and we're going to talk about the horsepower in a second. Well, I'll talk about it now. This is how horsepower was traditionally defined. And there's still different definitions of it, and that's why I say it's about 746 watts. If you have a mass, don't ask why, because I don't know, of 550 pounds, and you connect it to a pulley that a horse is going to use to lift this 550-pound mass 1 foot in 1 second, then that's 1 horsepower. Just turns out that that's the definition. It's a goofy definition, but science was not always as sophisticated as it is today. We go back even 100 years, 200 years, things were different. So, this is saying 42% is the useful power over the total. And I'm just customizing that formula a bit times 100. When you hit the gas in a car, what do you want the energy used to do? Move the car faster, right? Does the engine get hotter when you do that? Yes. Do we care about that? No. And I don't know how close to accurate 42% efficient is, but this is saying when you're driving around under most conditions, you get less than half of the useful energy coming out into doing what the car is intended to do. The rest is heating everything up. We've already calculated that this is 83,333.3 repeating. Was that the right number? So I'm going to cross multiply and get 42% times the total equals 83333.3 repeating times 100. So you have to take, for me please, 83,333.3 repeating times 100 divided by 42. When I multiply by 100, I actually multiply by 10. You should get this number. Excuse me. Let's just confirm something. If it's 42% efficient, if I multiply this by 0.42, I should get the energy used. It's right. So it's 198,413. Watts. But 1 horsepower equals 746 watts. So if we divide that total power in watts by 746, we get the horsepower of the engine. So about 266 horsepower. So cars are different now than they were, say, when I was in high school. I mean, cars were a big deal, like powerful cars and big cars and sports cars. You know, so we would often say, how many horses do you have under the hood? And that just means how many horsepower is driving this engine. So imagine 246 horses all somehow synced together, strapped to the car, pulling the car forward. That's what's representative of a 266 horsepower engine. All right, we have one more example to do. And then over tomorrow and Thursday, we're going to be doing a lot of review, and Friday is your exam. So we have a car of a mass, 2,000 kilograms, that's traveling up a hill at a constant speed. Okay. Is the car gaining any potential energy as the car goes up the hill? Yes, it's going up the hill. Is the car gaining any kinetic energy? It is not, because it's moving at a constant speed. So what is the forward force needed to maintain the car's speed? This is actually a dynamics question that we need to answer the power output. You need to know the force. So if we draw, 6 degrees. Now 6 degrees is pretty shallow. I'm going to draw it angled more than 6 degrees so it looks better. So it's easier for us to understand. And we have a car. It is going up the hill. And there is a forward force up. We need to know what this applied forward force up the hill is so we can find the work done, so we can divide by the time to get the power. How can we calculate this force? I'm asking you to reach back into the previous unit. Sam?
Would it be equal to the opposing force, wouldn't it?
Right. Which is a parallel component of gravity. There's also a force of friction, isn't there? And I think that's the first thing that your brain locked onto, right? That there is a force of friction of 450 newtons. But there is also a parallel component of gravity. If there weren't, then when you hit a hill, you wouldn't feel, I don't know how many of you drive or have driven on steep hills, but when you're driving on the highway and all of a sudden you get to a hill, like say in a mountain pass, you can feel the whole vehicle slow down suddenly. And if you want to maintain a particular speed, you really have to hit the gas. So there is also, this is a force of friction, there is also a parallel component of gravity. And all of these forces must balance if the car is to maintain a constant speed, because it's no acceleration. Well, let's calculate this. This is mg sine theta. I hope intuitively everybody understands that this is not going to be a really, really big number because it's only 6 degrees. Right? Imagine if it were 60-degree hill, which is nuts. Right? You're doing off-roading at that point, and you're going up mountainous hills. What's the mass? 2,000 times 9.81 times sine of 6. Make sure I'm in degrees, and I am. Does anybody else get about 2,050? It's 2,050.8. That means the total force backwards, oh man, let's call it 2,500. Are you with me on that, that you add those two forces together? This total force backwards is 2,500, and if you want to be pedantic about it, which means picky, we can include that 0.8. My addition's correct there, isn't it? That's the total resisting force, but I'm maintaining a constant speed by applying a certain amount of gas, and that means that this applied force forward must be 2,500.8 newtons. We did this so we can answer part B. Part B is, what's the power output? So power output is work over time. Work is force times displacement over time. Right. We know the force. We just calculated the force. We don't know the distance and we don't know the time. What can we do here? And there's a couple of options. Right? What can we do here? I'll give you a hint. What's this? Whoop. Didn't mean to do that. What is this? That's the velocity or speed of the car, which I think it said was 25 meters per second. I mean, you could put in a time and calculate a distance, but the ratio of the two is 25. So your power equals 2,500.8 times 25 meters over 1 second. Well, I don't know what that 0.8 is going to do, so I'll include it. Oh, no. 2,500 plus the 450. This times 25. 62,521 watts. Ish. And I think you're likely to see this on your unit exam, but maybe not with this much complexity to it. But if I told you that the force being applied up the hill by the engine was 2,500 newtons, this is a decimal, this is a multiplication. If I told you the applied upward force, you should reason out that you have to multiply by distance and divide by time, but that means you have to multiply by speed. And if you divide that by 746, this answer by 746, you'd get the number of horsepower that your engine needs to supply to accomplish this task. And if you don't have enough horses under the hood, you're just going to go slower and slower and slower until you find the speed that the horses can keep you at. And you know there aren't actually horses under there, right? Okay. Just, you never know.